Okay, so I'm Sam. I'm a PhD student with the CCIMI, and I'm working with Sergio. And today I'm going to talk about part of the work we've been doing on data augmentation, which is a tool for statistical inference which can help with understanding and efficiency. So to sort of illustrate the motivation behind it, I'm going to give a simple analogy. So when we're faced with a really basic task like this addition, anyone can write this down on a piece of paper, carry the one, and sort things out. But actually there's a bit of structure here which can make our life a bit easier. We notice that this first number is close to 9200, something with a bunch of zeros. That's much easier for us to work with. So we sort of add complexity to our model artificially in this way, and we notice that after we do this, it's going to collapse to something much nicer. And once we're done with this, we've solved the problem. So even though we've superficially made things tougher to start with, the problem that we have at the end is much easier for us. And this is sort of the idea I want to keep in mind with augmentation. So the framework we're looking at here is Bayesian inference. The main point here is that we have quantified uncertainty throughout our model in the form of distributions. We're looking at graphical models, which is a nice framework for encoding the conditional dependencies between a variety of variables. So we have a simple example here of a parametric family. So the idea is you sample some theta, which will characterize your distributions, and then conditional on theta, you draw each of these observations Zi. And the task we're ultimately looking at is sampling from the posterior of a distribution. This is a fairly standard task in Bayesian inference. Okay. So a more involved version of a graphical model is something called a mixture model. So a quick way of thinking about this is if you have a population of different categories which have distributions corresponding to them. So a simple model of this would be, say, human height. One might reasonably model the height of women as being one Gaussian distribution, the height of men as being another one. So the aggregate distribution for all human height would be something of this form. And we think of pk as being the sort of proportion of the population coming from each family, and theta k as being a parameter corresponding to that. So these are nice. These are very flexible. They characterize a bunch of uncertainty. But there are some issues that arise, right? So if we look, this is a mixture of 3 Gaussian distributions. One dimension should be nice, but already we have some things we don't want. We have multimodality. We have weird changes in curvature. So standard techniques of sampling will occasionally fail here, or definitely there's a way of doing it better. And if we quickly look, this is a mixture of 5 Gaussians. Again, we have sort of mild pathologies that we'd rather not have to deal with. But we sort of want to figure out how we can do better. So by analogy with the height case, we realized that if we had a data set of human heights and we knew what the genders were, we would just have 2 very simple one-dimensional problems. So by analogy with this, we can add in a variable to indicate what cluster we're in, which we'll call Z. So for each data point X, we'll have a Z which represents which cluster it comes from. This is the sort of hierarchical model structure we have here. And in sampling from the prior distribution, this is really simple now. We just say, pick a category, sample from that category. Each of these are very easy tasks. In practice, we want to sample from a posterior distribution as well. This is mildly more involved, but computationally still about the same difficulty. Right, so if we look at an extra pathological one, we have, I think this is 10 Gaussians with a bunch of spikes. Ultimately, by introducing these categorical variables, we can reduce it to the much simpler task that it secretly is, which is a combination of all these one-dimensional tasks. And that's sort of the idea. So data augmentations can be far more general than just these categorical things. So they can come from physical considerations. So occasionally you'll see statistical physics type models are very amenable to these. If you've ever used Hamiltonian Monte Carlo, this is sort of also a physical augmentation of sorts. Practical considerations like the one I just described. Also in Bayesian Nonparametrics, one will often be dealing with potentially infinite parameter spaces. That's not really tractable, so we have to find a way of dealing with those. And algebraic considerations. So this is when an augmentation will just make the likelihood or the posterior collapse into something far nicer to sample from. And I've got an application of this on the poster, which I'd love to talk to you about if we have the chance. And I think that's me done. Right.